here is one of a typical condition for the reference buffer. So for the SAR ADC, usually when you talk about the reference generation, right? So it could be power hungry. So here I underline a statement said the behavioral circuit can be very power hungry and even cause more power than the ADC itself. When we consider the reference buffer, the reference generation of the SAR ADC, so first, of course, you have the band gap over there. So those are not the power hungry guys. So I'm not going to talk about that. But then you will have the LDO and then you have the reference buffer. All right. So the buffer itself can have a good isolation between channel, and also it also help to give you some power supply rejection ratio. All right. So rather than just from the LDO, you will have more from the buffer. All right. They give you some, but it's not a lot. So usually you want the output buffer have a fast recovery to suppress the reference ripple. All right. So you want to have a low output impedance, very similar to what we have at the input buffer. But now you don't care for the linearity, which is good. All right. Or it provide a large reservoir to prevent the reference ripple. All right. So rather than you put a reference buffer, which is very low impedance, high transient kind of current, but now you can alternatively put a very, very large decoupling capacity there to make the ripple not happening at all. So here I just list a few reference buffer architecture. So one is the regular source follower, and the other is the super source follower, and the last one is the flipped around source follower. So due to the time limitation, so please forgive me, I just can briefly overview what that actually done. So here actually the GM of this guy, if you consider the body effect, then you have this one, the RR is equal to the 1 over GM1 plus GMB1. So usually these two is large, so whatever you have should be in this term. So if you talk about the source follower and the flip around voltage source follower, so you will have additional gain due to the feedback. So one of the gain actually is from here, because you have another path. So imagine you have something change up, then this change down, then this will also change up, right? So this change up, and then you also have pull down over here, so that you will have a kind of additional gain from this feedback circuit. So you will have also a times 1 over GM2 R not 1 terms factor over here. So the RR will be much smaller than this with the same amount of current, okay? Well, you can even do that with the same branches by cascading. So you fit the internal loop over here back to the cascade device, so that you can even have a even similar kind of gain boosting of the impedance over here. So so this will be equal to the 1 over GM1 plus GM2 times R01. So I would say these two architecture actually is more promising. Why they are not used in the input buffer? Actually, some of them are used, but the reason is because they have poor linearity usually. All right, so but they are good to use in the reference buffer because you do not have swing there. Okay, so these two actually is a good choice for the reference buffer. Well, the maximum operation swing of these few guys can be expressed in here. So you can actually take a look of that, but I just want to conclude the difference between them. So you can find that actually for the source follower, they do not have a very constrained maximum input voltage because you do not have a cascade device over here. So their maximum output voltage actually is divided by VDD minus the GM1. As long as this can saturate, this is good to have this maximum output voltage. And the input voltage just keep this guy being saturated with this VGS minus VTH overdrive voltage over here. So you can see that there's a huge kind of range you can make your input buffer can stay in saturation and operate very well if you are using a source follower, right? But of course, this is good for input buffer, may not good for reference buffer because the output impedance is not so low. Well, on the other hand, because of the cascode device, you can imagine you will have a poor maximum and minimum input allowable voltage. All right, so I'm not going to read them through, but you can look at that. So that's related to the VD set of M3 because you have another cascode device over here, and then you have to leave headroom, and then you have to make sure the input is being saturated. So that's why you have VDD minus VGS. So the flip around source follower will be very similar to from the maximum voltage point of view. So they are actually limited in a similar way because of the cascode device. But the flip around voltage source follower have another consideration with this VGS because now you have to keep this M2 saturated. So when you drop to the minimum input possible voltage, then you have to consider this VGS too also, right? So the conclusion is the allowable input range for the flip around source follower actually is less, all right? So it is very easy to make this reference buffer not work if you give a kind of extreme type of reference voltage over here, okay? So here get a little bit more range, but still is less than the source follower. So depend on the condition. Let's say if you have a huge range of reference voltage, then I would say you have to go for the source follower. But if you really consider about the output impedance, you should go for the FVF and the super source follower. All right, so here is a typical condition. We do it in a, we kind of extract every switching energy in every bit, okay? So here is a 10-bit VCM-based SAR ADC. In each cycle, it will consume different power, different energy from the switching. So that switching energy also proportional to how much current you draw from your reference buffer. Okay, so you can see that on the first bit, because it's only have a 1 or 0, so and then it's differential condition, so that's why it's always having the same kind of 1 or 0 energy from the first bit. However, if you go for the second MSB, then the combination of the first and second bit will make the story different, and it will consume a different energy, right? So let's say if you have 1, 0, 1 at the MSB, 0 at the second MSB, then you will draw more energy than the 0, 0 or 1, 1 case. So if you want to understand why this will draw more energy, I would suggest you to look at our paper. So we have a very rigorous analysis on that, but due to the time limit, I'm not going to go through that very detailedly, but you can get the idea that the energy consumed by the DAC actually is zero dependent. So that's why if you have a constant reference in output impedance, and then you will have a different kind of ripple. So that is the voltage drop in the initial condition of the SAR conversion. All right. So here you can see example when my SAR ADC is switching, then your first MSB will draw the energy from your reference voltage, and your reference voltage will drop initially, and then due to the it's more like the RC time constant settling, then you will recover if you give enough time. All right. So the recovery, it depends on the drop, right? So if you drop more, then you recover slower. If you drop less, you recover faster. All right, so here to give two examples, one is 101 and 001. You can clearly see that the settling actually is much different. All right, the problem here is the reference error is correlated to the ADC input because this code switching is dependent on the input. So it's highly signal dependent. And the problem is when you do a wrong comparison over here, you have no way to correct it in the digital domain because now your reference actually is changing code by code, cycle by cycle, and actually is settling afterward. So consider when you do a comparison over here, the reference for this bit actually is in here. And then after you do the comparison, the DAC will settle again. Okay, and the DAC is fine. The residue voltage is fine, but the comparison is wrong. And then this is signal dependent. So you have no way to find the problem and track the problem at all. There's a two type of reference ripple. So here's one example for the global reference ripple, I will call it. What is the global reference ripple? That is happen not within the bit cycling of the SAR-ADC. That is happen between the sample and sample. What is the problem is, let's say if you do a conversion, sample and conversion, and because you draw a lot of current, the charge from your input buffer. So your input buffer at this sample actually cannot be recovered back to a normal correct reference voltage. Okay, so when you do the next sample, you kind of have some ISI within this reference voltage. So what you will see is you will see a reference ripple that is related to your input frequency, totally dependent. So that means if you have certain input, then you have certain memory, then in the next sample, because of that memory, you kind of memorize the series sample condition, and then the settling is happen from that. Okay, so in that case, you will have a kind of ripple that is coupled to your input frequency. So you can imagine what that's going to be shown in the spectrum. That's going to be a tone, a harmonic that is related to your input frequency will show at the spectrum. Okay, so let's say if this is distort the circuit, let's say the comparator or whatever sampler, then that will modulate up to a different harmonic with your input frequency. Okay, so the other problem is what we usually consider is what we just saw before. Within the cycle, you have a different bit kind of switching. Then you will have a signal dependent, input dependent type of ripple throughout the cycle. And you will see in your histogram, ADC output histogram, here is the code count, here's the code count, here is the code you have. So in this case, you will see that you will have a large DNL over here and a missing code after that. All right, just adjacent to a large DNL, you will have a missing code. So this is happen is because, let's say, if you have reference ripple, then you cannot settle very well. And then in your next cycle, it starts settling again, but you already do the wrong transition. And then by that, then you go to the wrong transition, and then all the rest of the cycle try to recover these errors. They all go to the same direction, but still, you still have a missing code because you cannot go to the common mode or the ground voltage over here. So you will have a large code accumulate because there's a several input that will have the same condition accumulate in one code and some missing code due to you cannot touch the ground. All right. So by these two, you can see the problem of a SAR-ADC with this reference buffer and without a very low output impedance, then you will have this settling error. And you can see this code and this code is missing and add up together. So you can imagine there's no way you can do to identify the error over here because the code is mixing up. All right, so no calibration can be done. Well, actually, we have done a very prestigious kind of analysis on this problem. So here we kind of deriving the equivalent model for this VCM-based ADC and how this require how the requirement on the reference buffer, and if the reference buffer do not have enough output impedance, a small enough output impedance, and how it will affect the ADC performance. All right. So again, because this is very detailed, so I would suggest you go to our paper and read about that. But the idea is we based on a VCM-based switching, and then a reference look like this. Then we do a kind of a delta y, y to delta kind of transformation, so that we make this high order complex model to a more easy modelable kind of RC sampling network. So in this case, and then we do we simplify that. We use this model to give a impulse response, and how this impulse response is go through this equivalent kind of network, and how this impulse response react at the output. And with this output, then we can estimate the error come from the non-ideal reference buffer. Right. So you can see the equation is very complex. The top high voltage is equal to this VREF minus all bunch of this whole term. But here, what we have model include the on resistance, include the output impedance of the reference buffer, include the decoupling capacitance. So this is a little bit quite prestigious, I would say, is detailed enough model. It gives a good enough kind of estimation of the actual condition. Well, what actually is important is the result, all right? So we have used this result to try to plot what is the trend of this reference buffer. So here again, we have some assumption. We assume first the decoupling cap is small, only 0.5 picofarad, and then we talk about different resolution, 10-bit, 11-bit, 12-bit. So they have different sampling capacitance, 0.2, 0.8 to 3.2 picofarad. The input swing is around 1.6 VPP, and the DAC switching resistance out on is around 100 ohm. All right. Then we swap the output impedance of the reference buffer, and we swap the how much time we give for the DAC, the need for the DAC settling, and normalized, and do a normalized power in terms of how much factor of the RR we have. So here, give a 10-bit example, you can see that if we keep increasing the output impedance, all right, so we need more time for the DAC to settle, because the RC time constant is getting larger, right? So you need more time. And then, of course, by that, then you also will have some benefit from the power point of view. Well, let's say if you go for high resolution, actually this trade-off is more extreme, right? So you need a lot more power to just reduce to make you have small enough DAC settling. So you remember this scale actually is nanosecond. So if you want to have very fast cycling, then you need a lot of power, and this is kind of exponential relationship to make your output resistance more enough so that you can have fast settling time for the DAC. So your cycling of the SAR ADC will be fast. All right. So rather than that, as we mentioned, rather than we rely on very low output impedance resistor, what we can do is adding decoupling capacitance. So the figure in the right actually is the condition we add large decoupling capacitance. So this is the CDEC, all right? This is the decoupling capacitance. You can see that from the beginning, if we do not add any or just very small, then they will have a limit, the limit time, all right? So we cannot reduce the time a lot, all right? So it still need a long time, because in this case, we fix our output resistance of the, we do not have the reference buffer over here. We just purely rely on this decoupling cap provide the charge. And if we have small capacitance over here, then we do not have the pool. So we have wait for the reference to recover by its own. Then we have to wait for this long time. So as we mentioned, if we increase the decoupling capacitance, then the ripple can be suppressed, right? But there's an interesting kind of trend you can find here is if we increase just moderately, not large enough, it actually will make the settling even slower. All right. So the intuitive reason for that is because at this type of number of decoupling capacitance, this value, they do not give enough decoupling effort so to suppress the ripple. The ripple is still there. And now you add a low on the reference voltage. So the recovering of the reference voltage is even harder. All right. So in that case, you can see that there's a trend saying if you do not add enough decoupling capacitance, you will just make the thing worse. All right. Then you have to add a very large decoupling capacitance. Then you can have a short DAC time. Okay, so that trade-off is expanding for a higher resolution. All right, for even higher resolution, you can see the decoupling cap is kind of a double times or triple times in here. Okay, so with a very high, with a order of increase of the decoupling cap, you will consider this will come with a large area. All right, so this will be a huge area just for the decoupling. So eventually your ADC will full of capacitance and all the area actually spent on the decoupling capacitance. That is not a good idea. Okay, so I would like to remark here, actually this simulation is relatively ideal also, even though we model all the thing there, but remember, actually, if you have such a large amount of decoupling capacitance, actually, they are not as effective as simulation over here because now the decoupling capacitance consume area and you need some routing to whatever you have in the reference voltage. So this routing causes resistance. This parasitic resistance will reduce the effective decoupling ability so that your decoupling cap eventually could be even larger than this value. Well, there's some method to solve the reference voltage ripple problem. So first of all is the switching, and second is what we introduce the radix or redundancy over the conversion. All right, and the next one is do some isolation or compensation neutralization so that you make the ripple smaller. And finally, there's a cancellation method I would like to introduce. So let's do it one by one. So here is a switching method that can reduce the reference ripple. The idea is very simple. So in the SAR ADC, you first use a core SAR ADC to identify what type of input you need to do the switching. If you do not do the switching, you can still get the residue, then you just skip those switching. So by that, then you will save a lot of energy, plus you will draw less current from the reference voltage. Okay, so here is a energy pot versus different type of switching method. So you can see from the conventional trial and error kind of switching, they consume a lot of power. Then it come to different type of switching method. The VCM base give you a relative good balance between the switching energy and the easy implementation. Well, you can see that if you go to a what we call these different type of switching method like MCS or here the windowing type of method, then you can even have a switching energy smaller than VCM base. All right. So these two line actually is referred to here. Okay. So you can see that with this skipping type of switching, then you will save a lot of energy and then you will reduce the ripple from the reference voltage. Well, the other method is really adding an overrange. So the mechanism I'm not going to detail here because we will record it. We will visit this. We visit this later on in the following two lecture. But let's see. There's a two common way to adding redundancy in the SAR ADC. One is adding a binary capacitance, and the other is break this capacitance embedded with the MSB and corresponding LSB capacitance there, so that you can have a no diode range reduction. Because if you add a additional capacitance for the error correction, this capacitance will reduce your diode range because this will look like the parasitic over here now. All right, so this is just give you an example. Let's say for 10-bit resolution, if you add different redundancy, then you have a different kind of tolerance range, then you kind of reduce the you kind of make the tolerance of this reference ripple of your ADC stronger. All right, so you have stronger tolerance on the reference ripple of voltage, so that that actually also relax your reference buffer output impedance. Well, the other two method is doing the isolation. So you have a crossover cap which saving the reference voltage over here, and then when these DAC have to switch, rather than you having the reference, you draw the current from the reference voltage. Now you draw the current from this reservoir capacitor, right? So the poor thing of this is because you have this additional area, and these usually have to be large. And then this capacitor actually also is a separate version. So this is not embedded together with this CS. It attenuates the signal, and also it have a poor SNR in that case. And there's also another method to neutralize the reference ripple. So again, the reference ripple is because of the switching of this DAC. So let's say if you have a switch down from this DAC that draw the current from the reference voltage, if you have a compensation kind of capacitance that make the compensation charge from what that have to be drawn, and then that neutralize the reference ripple voltage over here, then this reference can be also stable, reduce the reference ripple voltage. However, this method actually require a very accurate kind of control. Remember, when you're switching this down, you have to instantaneously switch this on at the same time, so that it cancels the ripple. Otherwise, this ripple will still there, and or you compensate too much, or you cannot compensate enough, then in the comparison, you still got this error. So this is one of the problem, and it is very difficult to make this time edge being identical. It's because this compensation for one bit is easy, but for sequential bit, actually you do need a lot of different logic. So the delay of these two guys is purely not able to make identical. Well, there's some kind of trick you can do. If you have a deep trend cap, right, then you can put the deep trend cap under your DAC, so that this will more like a decoupling cap over here, and you can do a kind of a voltage regulation with a dynamic base, so that you remove the LDO, but now you have a comparator which compared to whatever reference voltage you want, and use the charge pump to pump the reference voltage to this trend cap capacitance. And this trend cap capacitance, the size is large, so that they can actually support whatever you need for the reference voltage. And because this trend cap capacitance is at the kind of lower layer of your capacitance, so the routing can be also short, can be effective. But this again rely on the technology. All right, so this is not so common. Well, there's also some other compensation method you can consider. Well, they actually use a coarse and fine kind of pumper, so that when you just need a coarse reference voltage, then they use a relative passive kind of condition. And then if you need a fine reference voltage, they have a loop similar to this one to make the reference voltage fine enough, and use the decoupling cap to give the charge over here. But you can see that because the mechanism is still rely on the decoupling capacitance, even though you make it coarse and fine, it can save some area, but still these look very considerable from the area point of view. Okay, so lastly is about the reference ripple cancellation. So the idea is quite interesting, I think. So the key point here is, if you have this reference voltage in your reference, if you can cancel it from the input, by that, then you will also have an ideal input over there. So how you can extract the reference voltage here is a good example how to do it. is, first of all, before the sampling, you pre-charge the ripple coupling capacitance to the reference voltage, okay, and the top pay to the VCM. And when you have the conversion, then you enable the ripple coupling capacitance by disconnect its top pay from VCM and then connect that to your current reference voltage. Remember, because you kind of saving a clean reference at the beginning, so whatever the ripple happening here actually will reflect directly on the top pay over here. So if you connect this top pay with a certain gain control to your input parallel with your input pair in the comparator, so this is more like a subtraction, your input will suffer from the reference ripple because of the reference voltage, but now you also add another input, also have this reference voltage, so these two cancel each other, so the reference ripple inherently is 0, all right, at the comparator input when you compare it. Okay, so I think this in order to make a very effective and very accurate kind of ripple cancellation, you can see this implementation actually add a lot of input pair to control the gain, because every bit actually have different kind of ripple amount, all right? So in that case, they have to add a lot of input pair in the comparator. So you can see that that will be certainly degrade the comparator speed. And another thing, actually, that will be very problematic is this method is not able to use in parallel ADC. The reason is because the ripple actually is canceled at the comparator input, all right? It's not at the residue. So your residue is still dirty, and only your comparison is okay. So in that case, when you hand over the residue is still dirty, so it does not solve any problem.